Tonight's speaker is Dr. Veronica Bray. Veronica is an associate staff scientist here at LPL. She got her undergraduate degree at University College London, her graduate degree at Imperial College London. And she's been at LPL for a few years. 9 years. Is a member of the science teams on at least 4 different missions, but the one she's going to be talking about tonight is New Horizons, the mission to Pluto. She joined that team in, you just told me, I forgot, 2013, and was there for the encounter, gave a wonderful talk last year. We asked her to come back since the data hadn't come down yet, so now she gets to talk about Pluto and actually show the data. So without further ado, Veronica Bray.
Okay. Please wave if I'm not loud enough. That sounds okay. So I'm going to be giving you a general tour of Pluto. We're still analyzing the data. As Tim said, it took a year to come down because the New Horizons spacecraft is so far away, the downlink speed is so low, and so we're just analyzing the full data set of images now. I wanted to start off with this introduction slide that shows you all of the different faces of Pluto, because as we'll go over, Pluto has a 6.5 day. And so because the mission was a flyby, we only got a good hard look at this face down here. So this is the famous one, the famous image. If you have any questions about things that you see on the rest of it, please ask me about that after the talk. But I'm going to be spending most of the time looking at the close-up face. Okay, so a little bit about my background. I'm a planetary scientist by training. I focus mostly on analyzing the surface geology of planets. I do that through basically looking at pretty pictures of these planets that we get back from satellite imagery, but also comparing it to field studies on Earth and also computer modeling of physical processes. My speciality is impact cratering, so what happens to the surface when an asteroid or a comet hits. And the science teams that I'm on is the LROC, the Lunar Reconnaissance Orbiter Camera, currently in orbit around the Moon. HiRISE, that's basically a spy camera taking excellent pictures of Mars. And then the Cassini spacecraft is just wrapping up its mission operations at Saturn, taking pictures of all of its moons. And then lastly, but obviously by no means least, the New Horizons, getting us images of the Pluto system. I'm also a targeting specialist for HiRISE, so I'm helping get some of the images which I can then analyze. The talk tonight's going to start off with just a couple of basics about New Horizons and Pluto, mentioning the available data sets, but due to my background, I'm going to be talking to you about the visual, like what can we see. If you've got some questions about the atmosphere or the plasma particles interactions that New Horizons does have data for, I'll try and answer them, but I'll probably refer you to a website. So without further ado, the geology review will be in a few slides' time after some basics. So Pluto basics. It's not a planet. It is a type of planet. Like this is just a nomenclature. When annoying scientists say that it's not a planet, what they mean is it's a special planet. It's a binary dwarf planet. So it's a binary planet because its moon Charon isn't orbiting Pluto around the mass of Pluto. Its moon Charon is so large compared to Pluto, here, for example, that they are orbiting each other, their combined center of mass. So Charon is also a binary planet with Pluto. The reason we call it a dwarf planet is because when we first discovered it, it was the first one of the Kuiper belt that we discovered and named, and then we started discovering all of these other similar sized, similar type objects in a huge belt around it. And so then we realized that we couldn't call it just a normal planet. It was reclassified as a dwarf planet because we understood it was in this massive neighborhood of other Kuiper belt objects. It's quite small compared to Earth. It's very, very far away. 248 Earth years is its one orbit around the Sun. I've mentioned its days, 6 Earth days. And it's the last of the classical planets to be explored. And that was one of the exciting things about being on the mission. It really did feel like this was the last place to go to look at, the last type of body that we hadn't seen yet. So pre-New Horizons, this is two of the best images we had, both Hubble Space Telescope images. This one's Pluto, Charon, Nix, and Hydra, 2 of its moons, or 2 of the system's moons. And then a fuzzy close-up of the Hubble image of Pluto. We could tell that it had albedo differences, light and dark patches, but in terms of its surface, we really were getting to Pluto with no idea what we would find there. So New Horizons, the mission that was sent to Pluto, it's an excellent, tiny, tiny little spacecraft. It's about the size of a grand piano. It weighs just 1 ton. It weighs about 1,000 pounds. And it has this brilliant suite of instruments able to analyze the atmosphere, solar wind, temperatures across the surface, the different compositions across the surface. The photos it sends back gives us the surface geology information. And it also has a student-led dust counter to tell us about dust that far out in the solar system. It was launched, so it's a tiny spacecraft, and we put it on the biggest rocket that we had at the time, the Atlas V. And so this was a tiny mission with a lot of oomph behind it. It was the fastest launch from Earth, 36,000 miles per hour. And that helped get us to Pluto in really quite a fast time, 9 years travel time, which was also speeded up by effectively slingshotting us round Jupiter. It gave us a gravity assist, helped speed us up and get us to Pluto faster. And because of that speed, we weren't able to slow down fast enough. We weren't able to slow down enough to go into orbit. That's why this was a flyby have It was a complaint that I've heard commonly. It's like, you just get one look. Why not go into orbit like all of the other missions that are out there? But it's because in order to slow down after this massively fast launch, we would have not been able to launch because of the weight of the fuel needed. We physically wouldn't have been able to get off Earth, and that's one of the reasons it was a flyby. So I'd never been involved in a flyby mission before. All of my other missions are orbiters, so it's lower stress. You know, if you don't get a piece of data the first time around, you might have the opportunity to go back and image again, for example. So it's a lot more high risk, high stress with the flyby. Another element of the flyby that is nerve-wracking is that it doesn't just fly past the Pluto system, it flies through it. So this is the trajectory of New Horizons, and then this is the orbit, the plane of the Pluto system, and it flies between the orbits of Charon and Pluto. Now, as New Horizons got closer and closer, every day we were getting images back, and a team of us would search the images to see, is there a moon or just a massive piece of rock out there or ice, anything that we might collide into, because then we'd have to change the course slightly. Another reason it was stressful was because with the flyby, all of the commands needed to be practiced ahead of time and given to the spacecraft ahead of time. We couldn't give it any commands when it was in the system. And one of the reasons for that is that the signal time from Pluto to Earth is about 4.5 hours. So we could send it a command, and 9 hours later we'd hear back from it, by which time it would be through the system. So this was all automated. So as it enters the Pluto system, it turned its antenna away from Earth and it concentrated itself purely on data collection. 13 hours of dead time, where we're just there wringing our hands, waiting to see when it's passed through, it would turn itself back to Earth and give us our call home signal, letting us know that it hadn't hit anything, and that the data was ready to be downloaded. And this was also the highest profile mission that I've been involved with. The media team were very, very good, possibly because Pluto is a favorite of the public. And so there was a lot of media interest, and that has resulted in quite a few embarrassing but nice photos of me thinking that I was on my own. This is me approximately 1 minute before the call home signal was expected. So I still don't know whether I've got a job the next day. This one was from an Italian newspaper, but there were loads of photographers following us around, catching those scared moments. Amanda looks very scared also. So this is a video of the approach. Oh, sorry. Now, remember that Pluto and Charon are actually orbiting each other, but that makes for a very queasy-making video. So in this, Pluto is centered. So all of these this isn't a simulation, this is all of the images that we took approaching Pluto. And there's the heart, Tombau Regio. And we're going to start zooming in towards one of the lobes of the heart, Sputnik Planum. You can see the dark equatorial belt here. The pole is just here. So it's slightly tilted. So this is now zooming into a mosaic from our closest approach image down into the highest resolution images that we have. Right at the edge of Sputnik Planum there. So you've got these massive icebergs and these polygons, and then straight into the highest resolution image. So you can see the kind of pitted nature of Sputnik Planum. And then out the other side, this is the last image taken from behind Pluto with the sun illuminating its atmosphere. Okay, so this is the improvement of resolution that we got from this mission. Okay. So this is the true color. So it's a similar color to Mars. It's the other red planet, very dusty looking in its color. But a lot of the images that I'm going to be showing you today are going to be enhanced color. And what this does is it combines the true color and the imagery with some spectral data. And that's to give us an idea of composition. So this is from some of the other data sets from New Horizons, the Ralph instruments, image in 4 spectral windows, and then we assign a color to each of those different images. And it will give us a reading of where are our concentrations of methane, of carbon monoxide, where is the water in the system. Okay, so this is the enhanced color compared to the true color. So it gives us so much more information than just the color alone. The polar deposits up here are a mixture of nitrogen and methane ice. And then the dark equatorial bands that I pointed out before, we know them to be tholins. They're complex molecules, and I'll go into their creation a little bit later. And then you can see actually with this compositional information that the heart is not just one feature. It has a distinct two sides to it. One of them is methane pore. The other one is a combination of methane, nitrogen, and carbon monoxide ices. And one of the things that we can see from this, if you ignore the very obvious feature, so just ignore the most interesting thing in this picture for a moment, we see latitude banding. So there's a distinct deposit at the pole. This area is then different, this is different, and then the equator is strikingly different. And part of the reason for all of the different layering is the orbital cycle of Pluto. Now, Pluto has an eccentric orbit. Sometimes it's much closer to the Sun than at the majority of its year. And so during the course of its year, its atmosphere will actually partly condense out, snow down on the surface, especially in the cold regions like the poles. And then during its summer, it will sublimate up again and give it a thicker atmosphere. And so we were expecting to see some blanketing of different ices on the surface, but we weren't expecting it to be interrupted by such an interesting feature and to see so few impact craters. And of course that was a slight disappointment for me, given that part of my job was to come and analyze these impact craters. But this is a fantastic thing for interest's sake, not for my sake, for interest's sake, because it means that it's a lot more active than we imagined. The older and less active a planetary body, the more impact craters you're going to have on it. Whereas, for example, Sputnik Planum, no impact craters, really fresh, really young, and it shows a more active Pluto than we were imagining. So I'd like to start the tour around the high-resolution pictures of Pluto with my personal favorite. It's a favorite for my personal reasons of it came down. It was one of the first ones that came down. I'm sorry, is there a question?
I was curious what time of year the flyby occurred. Pluto's year.
Oh, it was relatively close. It wasn't at its closest point to the Sun, which is... It was pretty much summertime, yes. So we could expect a thicker atmosphere and less ice on the surface than during wintertime. So we got this main image before closest approach, and then afterwards the data started coming back very, very slowly. And so the highest resolution data that came down first were in these red squares here. And one of the first ones to come down was this here, right in the middle of Sputnik Planum, which from the lower resolution images looked like it was about to be a boring white expanse of ice. Like I mean, obviously we're excited to see this new image, but we really weren't expecting that much. And this is what we got instead. There are a lot of big personalities on the team. Everyone voices their opinions very loudly, very surely, and then we'll all squabble over it and come to a consensus. I've never heard such silence in the room with those team members as this image got. After we got over the initial wow factor, of course, the joke was made. It wasn't the first thing that got said, but the first thing that got said to me was, well, Veronica, you might as well go home. There's no craters. But this shows us that this is one of the youngest surfaces that we know of in the whole solar system. And we weren't expecting Pluto to be that active. So we started trying to work out, well, what is this mass of polygonal shapes? What is the pitting? And why does there appear to be these, are they extrusions, exposed mountain tops? Like, what are these dark regions that are caught at the joining of these polygons? And what is the reason for the polygons themselves? You know, is it contraction cracks? Is it convection cells? So I like this photo because usually you just do your science quietly on your own. You don't have a camera in your face. But we started to get so used to the presence of a couple of photographers in the room that we did start to just be ourselves. Although you can see the people in the room that know the photographer is there. They've got their thinking look on. But the rest of us are busy having our discussion of what is this? And so we were each bringing up our personal experiences of what we'd seen on different planets and what we'd seen on Earth, like contraction cracks. Were the polygons because of expansion and contraction of the surface? Another person suggested this image, which is actually, it's about 3 meters across, and it's a picture that they took of a lake behind their house in Texas. And it's much more similar than contraction crack polygons, and it's because there's convection happening in the water beneath the ice that's kind of causing these little fractures and different temperatures in the ice that cause the polygons. Okay, so what we think is going on in these images of Sputnik Planum is that we have a convecting mass of carbon monoxide, methane and nitrogen ice, and that these pits that we see on it are sublimation pits. So as the ice heats up over its day, it will start to sublimate and join the atmosphere, basically, and it leaves these small pits. We think that these little mountains are floating icebergs that have carved off the surrounding bedrock, the bedrock being water ice. And then because of the convective motion, they slowly get drawn further to the center of Sputnik Planum. Okay, so Sputnik Planum itself, this is one of my favorite images, and we were just looking at the shoreline. Okay, so what we think is the reasoning for Sputnik Planum's existence is a massive impact. Of course, I'm thrilled by this because I see impact craters in anything circular or roughly circular. And so me and the other impact scientists, as soon as we saw that it is roughly circular on one side, we're like, oh, it's an impact. But fortunately, after a few months of argument and study, the team consensus is that this was initially formed by a very large comet impact, about 100 kilometers across, which formed about the 800-kilometer basin initially. But then that gives you a large hole in the ground, effectively. And we don't think that the ice is extrusive. We think that that occurred because this hole in the ground gave a much colder region and allowed a deep region so that when the atmosphere condensed, it would get trapped in this area and form quite a thick deposit of nitrogen, carbon monoxide, and methane ice. So then we have it convecting to form the cells, and then the crater rim probably would have been around here, I think, and part of the rim looks like it would slide down. We can't say for sure because this is an exceptionally old impact, and so we don't see very much evidence left other than its circular shape. Okay, so we do think that there's evidence around the edges of Sputnik Planum for the level of this ice deposit being higher in the past. For example, as it goes round and you get more deposition. So we're seeing it in summer. So during the winter, it might be that this sits at a higher level. And we think this is the main edge of, of obvious Sputnik Planum deposit, but you can also see it extending into the surrounding bedrock. And Elliott crater here also has Sputnik Planum on the floor. we don't think necessarily that this got that far. We think that Elliott crater is deep enough to form like a mini Sputnik Planum, effectively. But in the craters around it, it does look from their rims and the white deposits in them like they might have had bits of Sputnik Planum trapped in it, and then it kind of recedes back into its tidier bowl shape. Now, a closer look at that image to show the different styles of pitting that we're seeing. Sublimation is everywhere. It's a primary process on Pluto. So we think that these little pits here are sublimation in origin. But when we got to these larger ones, there was a discussion of, is this just a lot of sublimation pits kind of amalgamating into a larger one? We're not getting that impression because we only see these in specific locations. And so we'd expect if it was sublimation pits getting together and becoming larger, we'd expect to see them more frequently over Pluto. So what we think this is some sort of collapse pitting in the water ice bedrock. So maybe there's some sort of drainage going on in the subsurface which forms a void, and then the surface collapses down. Okay, so one of the another one of the first images to come down was this one, just on the edge of Sputnik Planum, and it's again showing us how active Pluto is. Amazing compared to what we were expecting. This was formed by an external event. An impact occurred and it allowed the atmosphere to create Sputnik Planum. But this, we think, is a cryovolcano. So this is telling us that Pluto is internally active. The funny and kind of shameful thing to admit about this image is that you have this very nice and now very obvious to us cryovolcano, and the embedded journalists in our room were kept saying, "It's a volcano. I think there's a volcano on Pluto," and we were all ignoring them because we were really excited about these relatively boring mountains over here. Like no one was bothered by that, and the reason we were really excited about these mountains, I'll give you a bit of a close-up here, is because, well, for another reason, this is mountain building is showing us, again, activity, but it's also showing us that this is the water ice. Nitrogen ice and methane ice, they're very weak, and so anything that's this tall, I'm forgetting, they're about 11 kilometers high, if memory serves. Yes, I think so. That topography couldn't be maintained by weak ices. So this was an indicator to us that this might be water ice bedrock. So we hadn't seen, on approach, we knew that Pluto probably had water ice as its main crustal component, but we hadn't seen it. And one of the reasons we hadn't seen it is because it's covered by other ices, so it's masked. We didn't see it in the compositional data. And because the images are slightly more interesting than the compositional data, we didn't get that data until 6 months later. And so we were having to search for clues for water ice in the images. So we were very pleased to see these icebergs tilt and show us clean water ice here. So just to give you a perspective, this is back on the edge of Sputnik Planum. There are the polygons. This is the older cratered terrain off to the side here, and a little glacier that was probably stuck there from a time when Sputnik Planum was higher. And this is some of the collapsing edge. And we think that all of the surface water ice is covered with a dark red covering of tholins, and you only get to have the water ice exposed when it has tilted in this fashion. Okay, so again, here's the edge of Sputnik Planum here. We're going deeper into the darker cratered terrain. And we think that this is still water ice, but covered with a dark layer of tholins. So tholins occur when you've got the presence of methane and nitrogen. They're basically destroyed in that molecular makeup by UV radiation, and they then kind of recombine into different compounds, different molecules, and basically rain down on the surface as these, I think somebody called them red space gunk, these tholins, these complex organic molecules. And when I say organic, I don't mean living, just we do see down here some small mountain chains, and we think that there's nitrogen ice, frost on the peaks of them. We think that Sputnik Planum has at least reached out to here, because you can see some in this crater. We think that this is one of the oldest terrains on Pluto based on the cratering density. You can see crater on top of crater here. Okay, so another example of one of the oldest terrains, perhaps even older, because it does have a high concentration of craters, but they're a lot more degraded. The ridges, the rims to these craters, you can still see are quite sharp. So that was just down here in Cthulhu Regio. Closer to the pole, we have Venera Terra, and we see evidence of ancient extension as well as ancient impact craters that have been degraded. This is, just for scale, like 3 to 4 kilometer wide valley systems. So of course that gets everyone excited, because as soon as you see a valley, are you talking surface fluid flow? We don't think that it was fluid flow, because some of the valleys have started off almost parallel, and in other regions they're clearly parallel. We think that there was ancient extension on Pluto, and then later these valleys, these extensional valleys, would have been widened by nitrogen ice glaciers going down them, widening and softening them compared to a normal fracture. Okay, we do think that there's still recent fracturing. So this fracture, for example, cuts the crater rather than the other way around. We don't find very many craters cutting this particular fracture system. Just for reference, we're now looking over here on the other lobe of Tombar Regio to a feature that we call the spider, unofficially. We think that this is a concentration of stress that causes radial cracks, and we do see this elsewhere in the solar system, on Venus, for example, and on Mercury. And using those as examples, our understanding of this feature is that there might be an upwelling of material in the subsurface, some hot diapir of material pushing the surface up and causing this concentration of fracturing. Okay, so now that you've had a quick tour around Pluto, I'm going to show you that first image again. Sorry, the first video again. It was slightly disappointing, well, it was incredibly disappointing to have a flyby mission, because as we're getting closer, there's all of those interesting features, possible massive impact craters on the backside, and we're never going to see that again unless we go to Pluto, and that again, and actually see the other side. So there's some of the very large fracture systems. There's one on Pluto's moon, Charon, that puts the Grand Canyon to shame. These are really gigantic features, and on such relatively small bodies as well. So again, out to the other side. It's our occultation image of Pluto. I have to admit, scrolling through my emails as the data came back. So we were on site at the Applied Physics Lab in Maryland for the encounter, so that we could all be there and watch whenever the images came down day and night. And then we all dispersed into our different institutions and carried on the data analysis remotely. This spectacular image came down into my email, and as a surface scientist, I looked at it and was like, oh, that's pretty, and carried on. Because there wasn't any data in it for me. I could appreciate the beauty, the significance of being able to turn around and photograph a different planetary body from behind it, looking towards the sun. But I didn't spend much time because I didn't think there was much data there for me. That is a zoom in of this no data. So just on the limb, there's so much data in this. There's so much information. And we just needed to stretch the image properly in order to reveal this, this horizon. This is the edge of Sputnik Planum, the massive glacier system, these hummocky mountain chains, cryovolcano, levels in the atmosphere, haze layers. And for me, this picture rates up there with the photo taken from the surface of the moon back, the picture of Earth taken from the surface of the moon. Like, this is a very worldly, Earth-like view of another planet, taken looking back towards Earth. Okay. We still have an extended mission. It has been approved. That's a good thing that I can finally say in one of these talks, is that the extended mission has been approved, so we're heading to another Kuiper Belt object to have a look at it. It's wonderfully named 2014 MU69, and we'll reach there as a New Year's present in 2019. There's so much that I didn't have time to cover in this talk. Please go here. We have blogs and the new images. We'll try and upload them as fast as we can. And if you have questions, please don't hesitate to email me. And thank you.
Questions? And let's see, do we have other microphones here in the back, or no? Okay.
If you were going to do another flyby,
Yes.
would you want to do it winter or summer? Would you want to see the same areas, or would you want to see different areas?
That's a really difficult question, because of course, it would be really interesting, especially from the atmospheric side of things, to see the same side during winter. I'd like to see the other side, because like I said, I'm the surface scientist, and all of that condensation, that snow from the atmosphere during winter is just covering up my landforms. So there's also a possible crater on the other side, which I had previously suggested shouldn't exist on Pluto, because the impact velocity is too low. And so as we were approaching it, this crater is looking more and more like that sort of crater that I said wouldn't be there. And then it turned and we missed it. So yeah, I'd like to see the other side of Pluto, definitely.
Other questions? She's coming down with a microphone.
Hello, hello, hello. Ooh, it's live.
What's the highest and lowest point on Pluto, and what's the largest crater that you found?
Let's try and go back to, this will be a while. That'll do. The two lowest points on this side is Sputnik Planum, is very low. Elliott crater also is one of the lowest points. Highest, I think it's actually some of the mountains around the edge, which makes sense, of course. If this is an ancient impact basin, you're going to have your massive dip in the middle and then very much a high around the ridges.
And what's the difference in elevation between them?
I don't know. I'm sorry about that.
Thanks. Sorry, I have to record this for the thing. Okay. Okay. So, one of the reasons that I hear Pluto isn't really like a real planet anymore is because it didn't clear its orbit around the outer solar system. If Pluto were located further in, would it be considered a planet like Earth and Mars and such, or would we still consider it a binary dwarf?
Does the rest of the Kuiper belt move further in with it, or does just Pluto move on its own?
Just if Pluto suddenly teleported to like near, like a further closer about Saturn,
It would be a binary planet.
It would
would
still be
lose
binary?
the dwarf. The whole reason for the dwarf is that it's in a big chain of material. For example, Ceres, the largest asteroid in the asteroid belt, was the first one to be found on account of its size, and it was named a planet. And it maintained planet status for about 80 years until they found the rest of the asteroid belt. And then they realized that they'd misnamed it and they called it an asteroid. And now because we realized that there'd been a mistake with Pluto also, we've now called them dwarf planets to cover quite a few examples in the solar system.
Just for my information, I know that there are two mountains close by that are named Hillary and Tenzing Norgay. I was just kind of curious as to what area of Pluto those are located at.
Oh, here, I think, if memory serves. This is the Hillary Montes. I might have a map of nomenclature. Where are we? Ah, there we go. These two, so they're right on the edge of Tombaugh Reggio.
Other questions?
Okay, I think you also have a map of Charon there. Some of the names seem a little unconventional, and is that in any way related to the fact that Pluto stopped being a planet just a few months after the mission was launched? Or is that just an evil rumour?
This for Charon, or no? This is sleep deprivation in action. We were up at all hours, and you have a team of nerds trapped together for weeks, seeing no one else, and so this is very obviously informal. But we had to, in our discussions, we had to call them something. So yeah, we allowed Charon to be our playground. So the full Star Trek team is in there, and Doctor Who gets a mention, and obviously Star Wars. We were a lot more serious with our naming for Pluto, but most of these names are still unofficial.
So for my question, just looking at the surface of Pluto with the abundance of ice, I was curious, is it possible that there could be potentially life underneath it, like bacteria or something?
On the surface, definitely not. The surface is about minus 400 Fahrenheit. There'll definitely not be anything there. In a lot of icy bodies, we have subsurface oceans. And so whenever it comes to a very, very cold planetary body, but you know that there's water under there, then maybe in the oceans you could have life form there. With Pluto, we don't know how warm that ocean would be, or well, even if it still exists. There's an argument between the modelers as to whether Pluto's ocean still exists. We don't think Charon's does. I'm kind of veering off here, but it's I'm glad to have the excuse to talk about this image. We think that in Charon's case, this gigantic canyon system was basically a planet-wide event where its subsurface ocean, which could have harbored life, or the beginnings of life, froze, and the expansion tore the planet. Dwarf planet.
Yes, you did mention that there were mountains around the Regio there that were up to 11 kilometers.
Oh.
Are those like the tallest, or have you discovered any that are taller than that? Because that would indicate, I don't know, 40,000 feet of relief on the planet. Then.
They're the tallest that I was there for the measurement of. I don't know if the people that are measuring the other topography have found anything better yet.
And how about the relief on Charon? Do you have any idea how much that is?
Where is it? I know that this is about 5 to 7 kilometers deep, just this one system. And the way that we got the measurement of that, it doesn't show up particularly well, but it extends all the way around. And so we could measure the notch taken out of the side of Charon. I know that that's 5 to 7 kilometers deep. Glad to have a number.
Yes. My question is, talking about the far side of Pluto, weren't there plans for seeing the night side of Pluto illuminated by Charon, a Charon light, which would have been very dim, but I believe wasn't the flyby time to take place at a time when Charon was illuminating the night side of Pluto, so one might have been able to see something.
We do have, where is it? We do have a similar version of this, but not of the full night side.
So you don't have any images of the night side of Pluto illuminated by Charon?
Not very well. I think there's some people that are still working on processing it, but I haven't seen any that came through and showed us very much information yet.
Okay, the other question I just thought of this moment, carbon monoxide ice has been found, has carbon dioxide, which is thermodynamically more stable relative to carbon monoxide. Has that been found on Pluto? CO2 as opposed to CO?
Not that I've seen.
Okay.
So what's the cryovolcanism putting out? Is that water magma or nitrogen, or do you have any ideas?
We're not exactly sure. We think that most of it is created with water ice, because that's the surrounding bedrock is water ice. But it's not magma as we know volcanism here. It's definitely ice and a fluid. I think water ice. But yeah, there's definitely still a debate going on what on earth is coming up out of Right Mons.
Other questions? Yeah, in the back.
How old perhaps was the impact from that created Sputnik Planum? And could you tell from perhaps the ridge that surrounds it by slumping or other such cratering processes?
We think it's one of the oldest features on Pluto, based on how degraded it is. You know, there's still the argument about whether it is an impact crater, and there's so much ice on the top of it and other craters superimposed and other fracturing. We think it's probably about 4 billion years old, so pretty much the same age as Pluto.
Thank you.
What percentage of information have you all received? Not necessarily analyzed, but actually received it. And are you anticipating more time being devoted to the complete analysis?
As of this month, we've got all of the images back. So it dribbled back to us over the course of the year. I think it's 1 to 2 kilobits per second, whereas normal home internet is 20 to 100 megabits per second. So it's really slow. And of course, the distance between Earth and Pluto is, rubbish. The distance between Earth and New Horizons is getting further all the time. So it was a very slow process, just over a year to get all of the images back. But scientists will be squabbling over this for decades. We'll never stop analyzing this.
Okay, I think that's probably a good point to stop on.